Screen's down here. 1 second.
I have a question. Is the homework and the homework solution supposed to be on the same page on the OneNote document?
Well, when we say page, it may be expanded, but they should be in the same area. Like, couldn't you see solutions?
I only saw the answers. I couldn't see the question. Yeah, I saw. You could tell what the questions were asking, but you didn't tell like the questions.
The questions were posted?
It would say like solve for, I don't know, H, but it would have H equals.
That's kind of what I'm asking you.
I'll tell you what, I'll check on that. Usually, I put the question or I give it, did I state problem numbers in there?
You stated the number, you had the question, and then it said solve for this, and then right next to it is the solution.
I can show you what it looks like.
No, I can look later, but the whole idea is this, that most of the homework is out of your text. So the numbers correspond to the chapter problems, and back is 6 in this one.
Okay.
And they should. And then for the solutions are, I think there were more solutions, wasn't but I will give you problems that aren't in the book, and I provide. Then I'll have the whole thing written out.
Okay.
But I'm sorry if there's any confusion about that.
Thank you.
Did you have any questions at all about the homework at all? Did I give you?
I had a question about let's see. The question that there's two questions, and the fifth part of each question, I was confused what it meant when it said the phasor domain. Is that, I guess I'm confused of which part of that complex is the phasor.
Which problem is that?
It was part 5 of both ones, so let's just do question 1, part 5.
All right. All right, 1, part 5. So, hoping one of these markers is good. Throw that down there. Remind me to throw that thing out. Otherwise, I'll hang around. All right, this one will work. All right, so this is part 5 of question 1. You give me the specifics?
Of the question?
Yeah. Because phasors always have magnitude and angle. That's how you tell.
Okay.
All right, time domain will have a cosine of omega t minus beta z. Usually, I mean, if it's a cosine waveform, plus or minus a phase angle. But go ahead.
I'm trying to see.
Relative epsilon is 72.
Okay, epsilon relative equals 72. Go ahead.
Sigma is 5,000. Relative mu is 1.
What's, mu relative, so it's non-magnetic, okay.
Right, and then the E field is 5.
What's the frequency? Is it given?
No, the frequency was.
Okay, go ahead.
5 e to the minus alpha z.
E is equal to, say that again?
E to the minus alpha z, the continuation constant.
Is there a coefficient here, E naught?
5.
Oh, sorry. You know what? I'm looking around. These are dying on me as we speak. Tell you what, I'm going to run and grab a few of these markers because they're usually in here. But these are dead. I'll be right back in a second. Anyway, yeah, the whole thing about this is the phase just has magnitude and angle, and we have a d to minus alpha z. But the time domain form is going to have the negative t in the cosine form. about that. I should have checked it before. So this is 5 e to the, what was it again?
Minus alpha z
Minus alpha z, go ahead.
cosine 2 pi times 10 to the 9th t minus bz,
Minus what?
bz,
Beta z. And that's it?
in the y direction.
A y. And what do they want?
Part 5 asks for the magnetic field.
Let's go through them all from part A. Part A is what?
You guys,
What?
I forget the name, is it?
intrinsic.
All right, before we get the intrinsic impedance, let's get a few basic parameters. How many of you know what the frequency is looking at that? Don't say. How do you get the frequency, anyone? You look at the coefficient of t, right? That's omega. So you know omega is equal to 2 pi f, and that's 2 pi times 10 to the 9th radians per second, or f is 10 to the 9th hertz. These things are assumed, but I want to go through it, right? So now that we have the frequency, since we have the intrinsic parameters right here, and I'd appreciate if you do this, if you have your calculators on it. Bring your calculators or use your laptops or whatever device that you have available, because it helps. We know the propagation constant is the square root of j omega mu times sigma plus j omega epsilon generally, right? Here's where we're going to check and see if this is a good conductor. So if it is a good conductor, a good conductor really has the conduction current is much greater than displacement current, or really sigma is much greater than omega epsilon. Does everybody follow me on this? Right? That's a good conductor when the conductivity is much greater than omega epsilon. Let's just see if it is. If it's of the same order of magnitude, you can't make this assumption. So I got sigma of 5,000. That's pretty good. And then I have omega epsilon. Let's just see what the relationship is. Omega is 2 pi times 10 to the 9th, right? Epsilon relative is 72. So it's going to be times 72, and then it's times epsilon naught. Now, epsilon naught can be rendered a lot of different ways. But for this one, I'm going to say 1 over 36 pi times 10 to the minus 9th, and that would be Farada's per meter. Y'all familiar with that? Whitworth uses that a lot. Now, the reason I did that is just to cancel the 2 pi and the 36 pi, right? I'll get 1 over 18 pi. Are you all agree with this? So I'm just going to put 18 down here. And now, when you look at this, I got 10 to the 9th, 10 to the minus 9th. That goes away, right? So I have 72 over 18, which is what? 9 over 36 is 4, right? So this whole thing is 4. And that means, in fact, the conductivity is much greater than omega epsilon, right? Now we can make the assumption it is a good conductor. Do you all agree with that? All right, if it's a good conductor, I know, and I believe if I didn't prove this, you tell me. If it's a good conductor, when you look here, you can assume that goes away, can't you? Because j omega epsilon is much, much less than sigma. Do you all agree with that? That means this, gamma, will be equal to alpha plus j beta. And I think I did this, but now it becomes what? Well, it becomes the square root of j times omega times mu times sigma. If you all see, I'm just trying to get through this little proof, right? And I know one other thing, j is equal to 1 plus j divided by the square root of 2, right? I'm going to go ahead and do it one more time. And that's times square root, omega is 2 pi f mu, right? And that means, when I look at this, square root of 2 in here, it becomes equal to 1 plus j times square root of pi f mu sigma. I'm glad we're talking about this, and that's gamma, right? And what can you glean from this, or by looking at it, you see how alpha and beta have to be the same? Y'all with me on that? Because, and that's critical. So here I know that alpha equals beta is equal to square root of pi f mu sigma, right? And now that I've got that, I can get whatever I want, but I've got those two quantities, and the question for part A was the intrinsic impedance. Well, eta is the square root of j omega mu over sigma plus j omega epsilon, technically, right? Do we need the j omega epsilon for this problem, class? No, because we've already established the conductivity is much larger than j omega epsilon. So we can just get rid of that. And here you can see that this becomes equal to, you can put it you can render it a lot of different ways, but this would be equal to square root of 2 pi f times mu relative is 1 times mu naught, right? Mu naught is 4 pi times 10 to the minus 7 divided by sigma. Sigma is 5,000, but it would be e to the j pi over 4, or at 45 degrees. Do y'all agree with that? Now, if you did the problem, this is just reinforcing what you've seen. By the way, what is that magnitude of this thing? Small. I can't tell you off the top of my head. It's 10 to the 9 times 4 pi times 10 to the minus 7, so 10. I don't know, it's less than 1, I believe. Anybody? Can you run the numbers? Just punch that in. It's 2 pi times 10 to the 9 times 4 pi times 10 to the minus 7 divided by 5,000. I don't know what that is. It's less than 1, though. I don't know how much it is. I can see myself too, which is useful because I can make sure I'm on camera. Anybody? By the way, the Starbucks in Louder is closed, but the one over in the Student Center is open. I don't drink a lot of Starbucks, but I do make that page. Anything, guys? It shouldn't be that tough, really. 2 pi times 10 to the 9 times 4 pi times 10 to the minus 7th, right?
I got 1.579.
Anybody else?
Like
Say again?
0.8.
Yeah, it's less than 1, but here's how you look at this thing. When I take a look at it's the square root of 2 pi, right? Times 10 to the 9th, then it's equal to times 4 pi times 10 to the minus 7th, all over 5,000, which is 5 times 10 to the 3rd, right? I just take a look at this for a second. I got 10 to the 9th, 10 to the minus 7th, that's 10 squared remaining, right? Divided by 10 to the 3rd is 10 to the minus 1. So we cancel all those, we get 10 to the minus 1 here. Then we see we've got 2 pi times 4 pi, or really 2 pi times 2 pi times 2, right? So that means we can take out this, I'll just do this over here. I can take out 2 pi, and then I can have it as the square root of 2/5, right? And then it's going to be times 10 to the minus 1. So that's 0.04 square root of that times 2 pi. Now tell me what it is. That's an easier.
Yeah, like 0.012, something like that.
Anybody else? You can divide this by 50 if you like. So it's 2 over 50. That's 2 over 2. Hey, that's 1 over 25, isn't it? So that square root of that's 5. So it's 2 pi over 5. Maybe it is greater than 1.
I'm getting 1.25.
Yeah, I'm believing you now. It's 2 pi over 5. Y'all with me on that? That was less than 1. So that would be, now that's in ohms. What is the characteristic impedance of this region at, say, 10 to the 9th hertz at air? It's that of free space. What is it? 120 pi or 377 ohms, right? So this is it's much, much less than that of free space. Do y'all understand that? That eta naught of free space? Maybe I didn't. maybe I'm assuming too much. Eta naught in general is equal to, or the intrinsic impedance is equal to J omega mu over sigma plus J omega epsilon. That's the general form for anything, right?
Mhm.
Now, if we are in free space or the atmosphere, we can assume that sigma is about 0. So I told you it's about 10 to the minus 14, 10 to the minus 15. It's about gone. So now the J's, we can say eta, if we assume sigma is much, much less than omega epsilon, is about equal to the square root of, well, the J's cancel, the omegas cancel, of mu over epsilon, right? Now here, if you look at this, mu is 4 pi times 10 to the minus 7th. Epsilon, this would be epsilon naught, mu naught. Epsilon naught is 1 over 36 pi times 10 to the minus 9th, right?
Mhm.
You do the division on those things, you're going to get a pi, and you're going to get a 120, or it's 120 pi ohms. So for free space, it's 120 pi ohms, or about 377 ohms. Remember that, that's what it is for free space. It's real important that you have a concept of that. My monthly T-Mobile bill. It's nice that we can let me know. Y'all with me?
Yes.
All right. Anyway, so this one is 1.2 something at an angle of 45 degrees, right?
Yes.
Important to put that angle on. So it's about that. What's the next part? I'll go through this one.
Propagation constant. Yes, propagation.
Well, we got that right here, right? Alpha and beta are the same. And what is this? Can you punch the numbers on that? It's square root of pi f mu sigma. So what do we got? I almost don't want to do this. What do we get on that one?
Your answer was about 4.41 times 10.
Don't trust me. Do it yourself. What did you get?
About 4 times 10 to the 3 multiplied by 1 plus J.
Okay, so it's about 4 times 10 to the minus 3, 1 plus J. Is that about right? Okay. To the minus 3?
I think it was positive.
I think positive. That makes sense. So that's saying that beta is equal to alpha, but beta is 4,000 radians per meter. That's a lot of wavelengths in here. What's the wavelength of this? Do I ask that? What's the wavelength? How do you always get wave? Don't put C over F. That's wrong. How do you get wavelength? People do that.
2 pi.
2 pi over beta. Very good. So 2 pi over beta. And what's that going to be? 2 pi over 4,000. So
4 times 10 to the negative 3.
say again.
1.41 times 10 to the negative 3.
All right, that's millimeter. All right, when you get down to millimeter waves, you're ultra small wavelengths. The reason is it's conducting. All right, that's the reason. 10 to the 9th. In free space, the wavelength would be C over F. So you'd have 3 times 10 to the 8th over 10 to the 9th, or 30 centimeters, about a third of a meter. All right, that's sizable. Right? This is trivial. What else do they want?
Phase velocity.
Okay. I like this problem. But yeah, this problem, it goes through everything you need to know and why you need to know. So what's phase velocity? There's a couple ways to get. The easiest way to get phase velocity is omega over beta. Yeah. Think about the cosine waveform. The irony of the cosine, you can always get that because you can take a derivative of that phase and set it equal to 0 and then solve for dz dt. And you get, and what's that going to be? That I don't know. 2 pi times 10 to the 9th over beta is, what is beta? 4 grand, roughly 4,000? About 4,000. So what do you get on that? That's going to be 10 to the 6th.
1.4 times 10.
What is it?
1.4 times 10 to the 6.
Now that's meters per second. What's the speed of light about?
3 times 10 to the 8.
That's slow. Orders of magnitude less than the speed of light. It's slow because you're going into a conductor. And I told you last time, real photons always move at the speed of light, but when they're ricocheting around a lattice, the net effect of propagation and direction is reduced greatly. And that's the reason for that. I always found that fascinating. Let's see, what else? Anyway, what's the next part? Sorry.
Magnetic field.
All right, and this is one that gets people, by the way. So I gave you the E field. How do I get the magnitude of the magnetic field? Now it's a propagating wave for starters, right? If it wasn't propagating, we can't do this. But we know what? Well, the ratio, magnitude ratio of E at a given point space-time over H is equal to eta, right? Magnitude of the intrinsic of piece. I just care about magnitude. I mean, if you want the exact value, we can get it. And maybe I'll show that next. But if I just want the magnitude, do y'all agree that that works? So if I want the magnitude of the H field, I'll go this way. I can say H is just equal to, magnitude-wise, the E field 5, right? Divided by eta. And eta was 1 point something, I think. Did I erase it?
I think the E field was millivolts.
Oh, is this millivolts? All right, 10 to the minus 3, so 5 times 10 to the minus 3. And what was eta, 1.2 something?
1.257.
257, so this is going to be pretty darn small, but you'll notice the E and H are comparable in magnitude. Usually E is much, much greater than H for free space. So what do you get for that one? 4 or 3 something? Times 10 to the minus 3. Anybody?
3.9, or about 4, if you're around.
About 4 times 10 to the minus 3rd amps per meter. What next? Oh, by the way, did they want the exact value for H? I'm going to show you a trick to get it.
It just says aging phasor dome, or the phasor dome.
All right, now that would probably imply they want magnitude and angle. By the way, that thing is off. Does anybody have a class in here? Maybe the thing won't blow up today. Here's the thing I want you to write down. I'm going to put it over here for a reason. These are very valuable for propagating waves, propagating plane waves, generally. I want to show you something. So for that E field that was given, I know that the E field it's a propagating plane wave. The E field in the actual time domain was 5e to the minus alpha. I'm just going to leave it as alpha. We calculated z times z. Then it's times the cosine of omega t minus beta z, right? And it's times 10 to the minus 3rd, and it's in the AY direction. Correct, class? Now, that is in the time domain. Now I'm going to put it in the phasor domain, right? So the thing I do is E, and I'll put a vector phasor here, is equal to, well, the magnitude of this, or I should say the real part coefficients, which is just 5e to the minus alpha z. We calculated alpha, right? About 4,000, is that right? All right, we calculated that. Now we simply put e to the minus j beta z. Beta is equal to alpha. We could combine those, but I'm going to leave them separately. We know beta is about 4,000, right? Times 10 to the minus 3 AY. Now the default units are volts per meter, so I'm not going to write that. Now, here's the trick to get H easily. You can say that I can take the curl of E and set it equal to minus dB dt, or really minus j omega times mu times h, and we could solve h by taking the curl, couldn't we? Y'all see we could take the curl of that, and then we could divide it by j minus j omega mu, and we could get h. That's a pain. I mean, that's the way you do it in general, if you don't know. The easy way to do this for a plane wave. This is only true for propagating plane waves. So if you have propagating plane waves, which is this whole chapter, and this is done all the time, then I can say that H can be gotten from E by taking 1 over eta. Now that's a complex number, so you have to include magnitude and angle. Then it's multiplied by a unit vector in the direction of propagation, and it's crossed in E. We're going to do this. So here, A sub P is a unit vector in direction of propagation. Okay? Now, I want you to look at this. Which way is that wave propagating? Which way is it moving? How do we know? It's the coefficient of this, right? If there's a minus beta z, it's going in the plus z direction. If it would be plus beta z in the minus, right? And the way you always get this is you take a look at the coefficient of the actual spatial vector. That coefficient is the magnitude of beta. If it's a minus sign, it's propagating in the plus direction. If it's a plus sign, it's going in the minus direction. Now, there's more to this that I don't want to jump into right now, but it doesn't have to be just propagating the z. It could be z and x. It could be zxy, and there we'd have to find the net vector direction and the net magnitude, but that's left. I'll do that at another time. Y'all with me in this class? So it gets kind of interesting. So here for this one, a unit vector in the direction of propagation would be, class, in the plus AZ direction. So you write that down. Everybody with me? Now we're going to go ahead and I'm going to erase the rest of this since I really want you to see this. This is perfect. I was going to do this. I don't think I did this last time. And this is a perfect lead into it for me. So I've got the unit vector in the direction of propagation. Now I want H, beats the heck out of doing curls. I take 1 over eta. Well, eta was 1 over, what is it, 1.2, right? And it's going to be at e to the j pi over 2, or pi over 4. It's 45 degrees, right? Mm-hmm. Right? I take that, I multiply it times AP or times AZ, and then I cross it with E. And E's up there, so it's crossed with 5E to the minus alpha Z, E to the minus J, beta Z times 10 to the minus third in the AY direction, okay? And this should be in the answer. Now, if you look at this for a second, you can see the 1.2 is strict real, the 5 is strict real, and 10 to the minus third is. So if I take 5 times 10 to the minus third divided by 1.2, that will be the magnitude. You all agree with that? And we did that a second ago over there. We found a 4, right? It was about 4 times 10 to the minus, I think it was, right? About 4 times 10 to the minus third. Now here's the important thing. What is AZ time, or AZ crossed AY? Do you all remember that? It's important you do. Let me do this. In general, if you have Cartesian coordinates, you have X, Y, Z. When you go this way, it's all plus. Then again, if you write it below there, and you go this way, it's all minus. Now here's what I mean. AX crossed AY is AZ. AY crossed AZ is AX, right? And AZ crossed AX is AY. You can do it with your right hand, assuming you have one. I got to be careful because there are people that have lost limbs, and so if you take your right hand and have one, and you want to know how to do the right hand rule, you take your index finger and you put it in the direction of the first vector. This is how you do it, cross products directionally. Then you use your thumb as like the hinge, it's going to rotate about. Then you cross it into the second vector, and your thumb will point in the direction of the cross product of the two. So if you had AX crossed an AY, it would be AZ. You probably remember that. However, if you're going the other way, if you go AX crossed minus AY, it would be minus AZ. And just keep that in mind. That's Cartesian. We could do cylindrical and spherical as well. Right? We don't do proloid, spheroid, or any of the other coordinate systems. We stick to the three basics. So cylindrical, Cartesian, and spherical. Those are the basics. Anyway, getting back to this, so we got AZ crossed AY is AX, right? Z crossed, AZ crossed AY minus AX, pardon me. So it's minus AX, right? And then, I'm going the other way, and then I'm gonna have still e to the minus alpha z, e to the minus j beta z. I know they're both about 4,000. There's one last thing. You see this angle? That's e to the j 45 degrees or e to the j pi over 4 radians. When we take 1 over that, it becomes e to the minus j pi over 4 radians. Are you with me? You all know that? If you have like 1 over 10 at an angle of 30 degrees, this is the same as 1 over 10 at an angle of minus 30 degrees, right? Whenever you go from denominator to numerator, the sign changes. That's the only thing I've shown you. Y'all, everybody okay with that?
Yeah.
So that's the H field. Now, is that it or is there more? All right, I'm going to continue. If I wanted the power, didn't I do power last time? Oh, I didn't. I'm just catching myself here. My notes. Well, first, are there any other questions about the homework before I start on? A logical thing was, this is kind of nice. I was going to cover that today about how to find H from E and E from H, and it's in the book. Here I'm going to put down the general form. I'm going to put it right next to this. For propagating waves, and this is for propagating waves. We find H is equal to 1 over the intrinsic impedance of the region times the unit vector in the direction of propagation crossed into E. And if you have H in 1E, it's minus eta times the unit vector in the direction of propagation crossed into H. So these are in your book. In that chapter, it's the relationship between E and H, knowing the intrinsic impedance in the direction of propagation. Do you see it in the book?
I'm not sure which page it is. Is it on
I can probably tell you.
power transmission?
No, that's going to be
That field?
It's page 327.
327. Okay. Early on, yeah.
Oh, there it is.
Yeah, that's it. And that's, again, make sure you put down plane waves. I want to make sure you say. It's true for spherical waves too, to an extent, but it's not exact. I don't think it's exact. That's the reason take a curl. If you're ever worried about getting an exact value for H, take the curl of E. And if you want the exact value for E, take the curl of H. Then you got it. Mathematically, you're going to be exact. All right, now those two are good. But when we have a wave propagating in space, there's a power density. And you can, where you experience this, anybody ever felt the heat lamp? Anything like that? What happens is, even though it's a very high frequency, short wavelength form of electromagnetic energy, the light causes that to strike your hand and you feel warmth because power is propagating through the air. And that's photons, all right? It's photons propagating. So when we take power, PAV, this is going to be the density in watts per meter squared. Before I do that, I always go back in the day when you had circuits, and you said power and for transmission lines was 1/2, right? It was 1/2 the real part of V, pardon me, V times I conjugated. Do y'all remember doing that? That was for power when you dealt with circuits problems, right? How much power was flowing. It was voltage times I conjugate, and you took the real part, right? In general, it boiled down to 1/2 magnitude of V squared over the magnitude of Z times the cosine of the angle cosine of the angle that Z made, right? The imaginary and the real part. But that's what you had there. And the units of power back in the day were watts, right? Now, when you have power density for a propagating wave, they use this symbol a lot, but Whitworth's book has PF. They'll have a script P there. That's called a Poynting vector. It's actually equal to 1/2 the real part of E crossed into H conjugated. I'm going to do that up here. All right. This is going to be for propagating waves. It's not for near fields. This is for propagating waves. It does work for near fields, but there's more to it. All right. If I take a look at this, I'm going to write this out one time and you guys will see it. Y'all with me on this? Can y'all see it okay?
What is the subscript for P? Let's say P.
Average, maybe it's just average power. You know how you have instantaneous power and average? This is the average power of the waveform because it's periodic. So if we take a look at this, I'm going to write this down. I can say P av here is equal to 1/2 the real part. Well, E, I'm just going to say it's going to be some E naught e to the minus alpha Z, e to the minus j beta Z. And I'm going to go ahead and call it in the AX direction. We'll assume the wave is propagating the plus Z and it's oriented in the X direction. If I can't make it more general, but you can adapt this, you'll see how. Then you have to take this and you have to cross this, that's cross product, with a conjugate of H. Well, H is going to be equal to E naught, I'm going to conjugate that, e to the minus alpha Z, e to the minus j beta Z, divided by magnitude of eta naught. Then the angle comes up here is e to the j eta naught, or an angle of eta naught. That's the intrinsic impedance here and here. And this would be in the AY direction. Let me try to explain what I've got here. I take this E field and divide it by the intrinsic impedance. I change the direction to be Y. Now, remember, this eta has a magnitude and an angle. This angle would be down here normally, e to the j, whatever that angle is. But because it's upstairs, it's going to have a minus, and I need to move that over just a bit. So it'd be e to the minus j angle associated with eta. I hope you can read that. You with me? You want me to blow it up for you? Okay, how about if I blow it up over here? That way you can see it. Average power, this is in your book, by the way, is 1/2 the real part of E naught e to the minus alpha Z, e to the minus j beta Z, that's a minus, all right, AX crossed into, and this is going to be conjugated, so it's going to be E naught over magnitude of the intrinsic impedance, e to the minus alpha Z, e to the minus j beta Z here. All right, that angle comes upstairs, so it's e to the minus j angle associated with that, right there. This thing is conjugated, and I'm going to talk about it. That's supposed to be an asterisk right there. Maybe you can't even see it. So this is supposed to have an asterisk, and you're familiar with conjugation, aren't you? Conjugate is what? Just flip the signs and the angles, right? So if I come here and I conjugate this, I just want you to watch this because I'm going to do it. When I conjugate this, the E naught stays the same. The magnitude of eta stays the same. The e to the minus alpha Z stays the same. But when I conjugate it, the minus sign jumps off of that beta Z. and off of that angle. Now I've conjugated it. Now here's the real bottom line on this. That means the average power density is much like what you found out from transmission lines. That's the power flowing, it would be in watts per meter squared, is equal to 1/2 times the magnitude of E naught squared over the magnitude of eta, that's the intrinsic impedance. Then it's times e to the minus 2 alpha z, and it's going to be times the cosine of the angle theta n, where theta n is the angle associated with the intrinsic impedance. Now, that angle right here is interesting, and that would be propagating in the AZ direction, by the way, because I had AX, and this should be an AY here. I had AX crossed AY has to be AZ, all right? And the units are going to be watts per meter squared. This is in your book. If you have your books, you can look there. I don't know the exact page, but I want to just mention a couple things about this. The angle here, if it's propagating in free space, that angle is 0, all right? If you don't have a lossy region, it means the cosine of 0 is 1, right? Now, as you get into a better and better conducting region, it becomes closer and closer to 45 degrees. So the worst case, when it's 45 degrees, that's a really good conductor. The cosine of 45 is 1 over the square root of 2. So that's the range. Follow me on that? It's not terrible, but it's enough that you have to pay attention to it. The main power loss always comes with e to the minus 2 alpha z. That's where the thing just decays down to 0. But that is the power flowing in a propagating wave. And what's nice is in free space, if you're talking about free space or a lossless region, the average power density, and I love this, is just 1/2 magnitude of the E field, E naught squared over eta, and it would be in a direction propagation. That's really nice, because in free space, it's just E field squared over 2 over 120 pi or over 377. So if you have E, you've got the power density, and you have H also in free space. And if you have any one of the others, you have all of them. All right, so that's power flow. Now, doesn't that remind you of the power flow that happened in transmission lines? Remember, you had the e to the minus 2 alpha z, and there was the cosine of the angle. It was awesome. The bomb. In a way, it's good. It tells me I got about 15 minutes. Wait a second. No, I got more than 15 minutes.
About 30.
30. All right, so that's in watts per meter squared. Next, we did the loss tangent last time. We talked about that. It's just useful. Now, we got to talk about, when we deal with conductors, do you all remember skin depth? Did you have that in EMAG 1 or not? No?
No.
Okay, well, we're going to get into something, how the actual good conductor prevents signals from getting internal to elements, and all the resistance has to do with the skin. You're going to see it in 1 second. I don't think we have any rain in the forecast, do we? I kind of wish we would get rid of some of this pollen. Okay. So now we're talking about how, or what the effects of a good conductor are on things like resistance. So this is going to be for good conductors. And we're we're gonna take a look at something. We have a good conductor, alpha is equal to beta. And if we look in general, we know the E field is some E naught, e to the minus alpha z, e to the minus j beta z. You might as well just call it in the AX direction. And if you plotted that versus distance x, or I mean z, what you find out is the E field itself, this is going to be the E field. It would do this. And this would be proportional to e to the minus alpha z, right? I'm just stating the obvious. Now, when we have a resistor, let's just think about this. We have a resistor like so. F5. And we know that the thing has a radius of a. It has a cross-sectional area of pi a squared, and it has a length L, right? Then you probably remember doing this in EMAG 1. This is a classic problem that in order to calculate the resistance, you usually start off, you assume I, right? You assume I, so you're assuming a current I flowing there, coming back here. And it's flowing and it's equally distributed across the cross section. Second thing is you get J is equal to I over pi a squared over the cross sectional area. And it's going to be in the AZ direction. You're going to make this Z, right? And then the third thing you did in EMAG 1 back in the day, you found the E field because you know that J was equal to sigma E. This is low frequency or DC. And therefore, the E field itself was equal to J over sigma, or it's I over pi a squared sigma AZ. Y'all remember doing this stuff? Then the next thing you did was find the voltage between this point and this point. And you got that by saying the voltage was equal to the integral of E dot dl from 0 to L. I flipped the signs on this one, so it's already there. It's going to be a strict real value, strict positive value. And that's really just going to be the magnitude of E times the magnitude of L. Y'all with me in that? If the E field's constant, then if you want the voltage between 2 points, you integrate the E field and you find it. When we talk about resistance, it's strict positive, correct, class? So I get this, and then I find the resistance, and that was equal to V over I. And here you can look. When I do this, there's my E, right? Right there. When I multiply it by L, I get an L up here. And if I divide by I find out I get L over pi a squared, right? Divided by sigma. Or really, it's equal to 1 over sigma, the ratio of length over area. Now that's the DC resistance. Do y'all remember doing that? Okay. Now, here's something that happens when we have a good conductor. We take a look at this and there's an E field on the surface, but we know that as the E field penetrates in towards the center of the wire, it's decaying. Do y'all see that? Right? But we term something, we call it the skin depth. We talked about something called the skin depth, and that's where the value here goes to e to the minus 1. All right? Its original value. In other words, let me try to be a little more clear. If I take a look at just the magnitude of the E field versus Z, it's equal to some scalar value times e to the minus alpha z. So if I take this quantity and make it equal to e to the minus 1, basically z is then given the distinction of being called the skin depth. And it's simply 1 over alpha. And that's the value when all of a sudden, when the E field will go down to e to the minus 1, or about 33%, it's a peak value. Do you follow me? Now, you can prove this, but if I go ahead and I say that all the current, let me do it this way, so you can understand what I'm really talking about. If the skin depth is less than A, that's the first thing, it has to be less than A. If that's the case, then the actual resistance, this will be an AC resistance, will be equal to, it'll still be proportional to length, but the area now will only be this annular ring. You all see that? So it's still proportional to length, still inversely proportional to sigma, but now, well, what is the area? And here's how I like to explain it. When I think about that area, try to do this. I say that we're looking right down the cross-sectional wire. If this is radius A, and this thickness is going to be a skin depth here, then this area that I'm chalking off like such, that area would be the area of the entire wire, or pi A squared, minus the area of this internal portion, or minus pi times A minus the skin depth squared. Does that make sense to everybody? Mm-hmm. All right, I'm going to just show you an approximation that's used all the time. When I do this, what do I really get? I find that the reduced area would be pi stays out front. I have A squared minus, and then it's going to be A squared, right, minus 2A skin depth plus skin depth squared. You all agree with that? Mm-hmm. I just expanded that A minus skin depth squared. Here I can see the A's cancel, and I'm left with an area of pi times 2 pi A skin depth plus skin depth squared. And usually the skin depth is much less than the radius, so we say that that area right there is about equal to simply 2 pi A times the skin depth. And the skin depth, remember this one, this is the skin depth. The skin depth is equal to 1 over the square root of pi f mu sigma. It's really 1 over alpha, right? And alpha is square root of pi f mu sigma. If it seems like it's coming at you real fast, you'll catch up. You'll be using this stuff to do many, many problems. Skin depth will be second nature. It's like F equal ma in physics, right? You'd use it so much, it just sticks in your brain, you can't help. Or V equals IR. That's the skin depth. Remember, if skin depth is less than the radius, then you have to use that formula. And generally speaking, what they do is say this. For AC resistance, if the skin depth is much less than A, which is a lot of times the case, then you say the resistance of anything with a constant cross-section is given as the length over sigma, always that, but then they approximate it as 2 pi A skin depth. Let me tell you where they get that. They say, well, if I cut this and just stretched it out, it would have a length of the perimeter, or 2 pi A, right? And the thickness would just be a skin depth. It's like a long, thin strip. You all follow me on that, class? Mm-hmm. All right, so that's where they get this, and that's the AC resistance for a wire. Now, in Wentworth's book, he's going to give you problems where he's going to have pieces like hollow pipes. He's going to have conducting, and I'm going to give that to you, but he's going to have basically a type of transmission line where you have current flowing down the inner core and coming back on the outer cladding. And you have to find the resistance per meter, which means you have to find the resistance per meter of the inner one and add it to the resistance per meter of the outer one. Y'all follow me on that? You probably had to do that in EMAG 1. I'm just going to set up a problem for you. trying to get the reflections from surfaces, normal incidence. There's only two people who drinks, three. I'm sorry. I'm telling you, a cup of coffee after lunch is necessary usually for me if I didn't get enough sleep last night. I have a sandwich or something, I'm ready to.
Yeah.
By the way, I never think professors are exempt from that or anybody in administration. I've been in meetings with some of the top level people right after lunch. And if they don't serve coffee right away, I'll see this. I mean, it doesn't matter what your pay grade is. Everybody's susceptible to that. Because most of these guys they got to get up real early. And, they're up at 5:36. By the time they get done with their lunch, that's usually 12:30 or 1:30, they're sitting there. And if they don't have coffee, I'll see this. Okay. Now, here's a typical problem. He's going to have an outer pipe, like so. You can imagine this. And then he's going to have an inner core, like so. This thing will have some radius A, this will be B, and this will be C. I think you can all envision. It's a thick pipe, right? Mm-hmm. Now, current is being driven in a differential fashion, which means current is coming down this way, and then it's coming back on the outer cladding, the same amount of current. Y'all with me? We want to figure out the AC resistance of that, assuming both have conductivity sigma. If this was different, then we'd have to use a different conductivity here and here. Y'all with me? So we would say the resistance per meter, R per meter, I should say it that way, R per meter, would be equal, well, the resistance of the inner one per meter, the length would be 1 over sigma, and then it would be equal, and we're going to assume something, assume the skin depth is much less than radius A. So in other words, it's just a little bit. Now that's going to be over 2 pi A skin depth. That would be the resistance of the inner core. Then the resistance of the outer core, and this is something that oftentimes people don't teach students. The electric field, if this thing is being driven in a differential potential, so there's a minus on the outside of grounded, and the inner one has got a positive. Just think of it that way. The electric field is set up here. It's set up between the inner and outer conductor, but it's not set up on the outer portion, it's the inner portion. Think of a capacitor. Right? So there will be charge on this rim and opposite charge built on there, but not out here. So then that means the second resistance per meter would be 1 over the sigma of the outer conductor, and that would be 2 pi, what would the distance be that I use? 2 pi B, right? Now I'd use the radius of that outer part, 2 pi B times the skin depth, and that would be the resistance per meter, not 2 pi C. That's the point, okay? And that would be all that area right there that's flowing through, right? Just outside the rim. All right, I'm doing that. I'm giving away some answers, but I want to make sure everybody's clear on it. Yes, sir?
And you're assuming the length is 1?
Yeah, it's per meter, so when we do per meter resistance, just put L equal 1. That's easier to do, right? And I don't give it just, in a lot of Dr. Wentworth's book, he'll have L. And if you don't need it, I mean, if you're going to be per meter, just leave L as 1. That way you can't mess up. All right. Next. This is good. Now we get into something that's equivalent to terminated transmission lines. Remember, when you had a transmission line, you first start with an infinitely long one. You went ahead and you developed the equations for voltage and current, and then you terminate it. You got the reflection coefficient, so you could do real problems, right? Same deal here. Now what we do is we say we're going to have two media. Call this medium 1. And then here's medium 2. Now let's make them lossless for now. So here, and this is smart to always do, anytime you're given a choice to where to put a natural boundary between two regions, here's medium, put it at z equals 0. I mean, make it 0. Don't make that z equals 2.5 or something. Because you're the guy that's choosing the coordinate systems. I want to choose a Cartesian coordinate system where that's 0 and that's going this way. Now, what I'm really talking about when I talk about, and this was going to be reflection, and this is going to assume normal incidence. What normal incidence means is we're going to have an electromagnetic field that's propagating in this direction, and it's going to hit this at a 90-degree angle. It's going to slam in like dropping a pin into the floor. It's not coming in at an angle that's oblique, where it's less than 90. Y'all follow me? So it's coming in at 90. This would be my incident E field. Now, when this field hits, it's going to also reflect, and there'll be a reflected E field. E reflected. Call this the X direction, by the way. And there'll also be a transmitted electric field. And this would be E transmitted. Y'all with me? That's just the electric fields. That's as easy as I can get. So when I take a look at the incident electric field, it would have some value E0, call it I, e to the minus j beta 1 z in the AX direction. And it would have an H field, an incident H field. Now, do you remember how to get the H field? We could take what? 1 over eta, right? And we could take a unit vector in the direction of propagation and cross it into the E field, right? Here's a little trick. When you're dealing with propagating waves, E crossed into H is always the direction of propagation. Always. So, E is in the X direction. Which way is it propagating? Positive Z, right? It's the coefficient there is a minus J beta, right? That's got it in the Z. So it's positive Z. So E, right, crossed to H has to be positive Z. H has to be HY. Y'all follow me on that? Think about it. I got E in the X, crossed into something Z. That something's got to be Y. That's the way I think about it. So that means the H field, its incident would be that E field, E naught incident, over eta, right? Whatever eta 1 is, the intrinsic impedance or region 1, e to the minus j beta 1 z in the AY direction. Now, eta could be complex, but I'm assuming it's lossless, so it isn't. That's the incident field. When I take a look at the reflected field, that's going to be equal to E naught reflected, e to the plus j beta 1 z AX. It's the same. I just copy that down, accept the exponential here. Then it's going to be H reflected is equal to E naught reflected right there. And if I can't use, you know what? I think I did this last time. Do you remember when I said the ratio of E naught plus to H naught plus was equal to the intrinsic impedance. Do y'all remember that? I think I said this, that the ratio of E naught minus over H naught minus was minus that. Do you remember that? No? How many do? Kind of, sort of, huh? Well, the reason it comes out to be a minus, if you go through the equations, the curl of E equations, when you have a wave traveling in the negative direction, right there, you take the curl, it pops out a positive J, not a negative J, and you're going to be left. This is going to be positive, the ratio of the two. This will be negative. Just trust me on this one. So that means the reflected field is going to have minus E naught reflected. Remember, circle that minus sign over eta 1 e to the plus j beta 1 z in the a y direction. And finally, the transmitted field, it'll look pretty much like the incident field. E naught transmitted, some scalar value, times e to the minus j. Now this will be beta 2z, beta 2 because we're in the second medium. And I didn't put this down here, but this has some eta 1, beta 1. This has some eta 2, beta 2. And one thing I should always say, the frequency is always the same for propagating waves as they penetrate different regions. Always the same frequency. Wavelength will change, and beta will change, but never the frequency. So this is the transmitted wave, and it's going to be in the AX direction. And the H field transmitted will be equal to E naught transmitted divided by eta 2 times e to the minus j beta 2 times z in the AX, or in the AY direction. AY direction. All right. So I've just restated and said what E and H are for the different incident reflected waves, right? Now, do you remember the thing called boundary conditions back in the day when you were taking? You know, there are two critical boundary conditions, assuming there are no surface currents. One is the tangent E field on this side has to be the tangent E field on the other side of the boundary for a planar boundary. And you also knew that H tan 1 was H tan 2. Do y'all remember that? So when we go ahead, and I'll do it right here, when we take E tan region 1 equal to the tangent component of the E field in region 2, we get, well, here this occurs at z equals 0, right? Because clever person that I am, I made sure that I knew that these exponentials would go to 0. Do y'all see that? When z is 0, go to 1. E to the 0 is 1. So then I have E incident 0 plus E naught reflected. That's, remember, these two at this point would be the reflected and the incident wave have to be equal to the transmitted wave. E naught transmit, that's the first equation. Then when we take H tan in region 1 equal to H tan in region 2, now we get E naught incident over eta 1 minus E naught reflected over eta 1 is equal to E naught transmitted over eta 2. And that should bring back kind of memories of when we did this stuff for the actual transmission. It's something similar. All right? So I get this. I've got two equations. I've got this equation. And I have this equation. But what I really want is to solve for a ratio of the reflected to the incident field. So if I take E naught transmitted and put it in here, then I'm going to take this, becomes E naught incident plus E naught reflected over eta 2, right, is equal to this. Now I have E naught incident, E naught reflected, eta 1 and eta 2. Y'all with me? You don't have to look at this middle part, right? Now I can go ahead and divide both sides by E naught incident. And if I do that, I'll do it over here. Now I get 1 over eta 1 plus, and here I define what I've been waiting to do, the reflection coefficient is symbolized by that, and it's E naught reflected over E naught incident. It's a ratio of the reflected to the incident field's magnitude. So that becomes the reflection coefficient is equal to 1 plus reflection coefficient over 82. And the only thing I've done there is divide top and bottom on that first equation by E naught incident, replace the ratio of E naught reflected to E naught incident by the reflection coefficient. Now y'all see, I can go ahead and multiply both sides by 82 eta 1. Then I can organize things, but here's what I'm going to get. At the end, I'm going to get the reflection coefficient equal to eta 2, the impedance I'm going into, minus the impedance I came from, over the impedance I'm going into, plus the impedance I came from. And that is something very important. That's the reflection coefficient. All right, now doesn't that remind you of transmission lines where, if you want the reflection coefficient, you took Z load, the impedance you went into, minus Z naught over Z load plus Z naught. Go with me? Furthermore, we can also mention, I will, that the standing wave ratio you remember what SWR was? I just got done with teaching this to my the other class. The standing wave ratio is really E max over E min in the phasor domain for waves propagating. Do y'all remember that? Back in the day, you had V max over V min on the transmission line. It's the same deal here. And here's what's going on. I got electric field coming in here. It hits, some of it's reflected. Well, the superposition of the incident reflected wave cause a pattern like this. All right? Where there'd be a maximum minimum. For instance, if this is a perfect conductor, then the electric field would short out to 0 there. And therefore, the reflected would be the same as the incident field magnitude, but it would be opposite sides, so you would get 0 E field here, twice the E field, exactly a quarter wavelength away, if you remember that stuff. Now, I'm not going to get into it right now. Well, for this, the ratio of maximum to minimum, I'm just going to put it down because I'm out of time, will be 1 plus the magnitude of the reflection coefficient over 1 minus the magnitude of the reflection coefficient. Now, I don't remember how much you know about, I don't know how much you remember about standing wave ratio, but the maximum value a standing wave ratio can have is infinite. Because if gamma is 1, 1 minus 1, and it can be 1 easily, is 0, it's going to infinity. And the lowest possible value is 1. That's when the reflection coefficient is 0. When the reflection coefficient is 0, then I got 1 over 1. So that's what you always strive for, is to get a standing wave ratio of 1 or a reflection coefficient of 0. Because I'm talking about when you're dealing with things where you're trying to propagate electromagnetic energy through, you never want anything reflected. You're trying to get everything into the system or propagating away from the system. And that's 2:31 and a few seconds according to my watch. Are there any questions about this? I'll stick around long. I just wanted to get that up there. I want to give you some problems. And I'll tell you one thing, you'll see a lot of parallels with email 1 right here. And I'll give you more problems. But if you have questions, ask me. Thank you for recording it. I hope it's done.
Thank you.
I hope this works.